welcome to the weekly colloquium. Today, the speaker is one of ours, Rajendra Bhati, who has joined CTP December last year. Let me briefly introduce Raj, since I think this is the your first public seminar in CTP. So maybe a few words of introduction. Rajendra graduated from Indian Institute of Science, Education and Research in Mohali, India, where he also did his PhD in the same institute. During PhD, he worked on weak value paradox and contextuality, as well as objectivity and spectrum broadcast structure, which I imagine is the subject of today's talk. Later, he decided to have some industry experience, and he worked in a Bangalore quantum startup, which was called Quantfluence, where he worked on a characterization of a continuous variable, of a model of a continuous variable teleportation. But then, fortunately for us, he decided to come back to science, and since December, Rajendra joined TTP path on.
So they didn't make any money.
On project, or maybe you pay better money. That's the second option. Okay, Raj, the floor is yours.
Thank you guys for long introduction. Thank you everybody for joining. Today I'm going to talk about work I did in my PhD. Work is related to try to argue that a position basis in quantum mechanics or in nature is somehow preferred by nature or any dynamics we encounter in our nature. So before delving into let's try to see why quantum mechanics is so peculiar. So let's revise the postulates of quantum mechanics. We begin with states and observable descriptions. A vector is fully described by a state of a system is described by vectors in complex Hilbert spaces, and observables corresponds to Hermitian operators acting on these Hilbert spaces. And the time evolution of such systems are given by Schrödinger time evolution equation, which is reversible and unitary, which generates unitary dynamics. Whereas the measurements are characterized by certain collapses. Whenever an observable is measured, the system collapses to one of its eigenstates, which is known as state update rule, and the probability of outcome is given by the Bond rule. Then the fourth and one of the most important postulates is the composite system postulates, where it makes quantum theory scalable and universal to macroscopic level. So the state space associated with composite system is described by tensor product of the subsystem in Hilbert spaces. So now let's see what are the consequences of these postulates. So superposition of classical realities are somehow implicit from the first postulate of quantum mechanics. So states in Hilbert spaces are in superposition of certain distinguishable states, which we call basis states. So suppose there are playing cards, which can take four possibilities, and our observable is what is the suit of the card. So it can have four possibilities, and a state, according to quantum mechanics, can be found in a superposition of all the state which we can encounter. So the question when we have this state and we have not measured yet, then the question which suit is has no physical meaning, and that somehow we will come to that that's somehow related to complementarity. That when we talk about certain observables, we cannot talk about other observables. Then similarly, a particle can be in superposition of different positions, which is not observed in our classical world. So a particle is in, let's say, in superposition of different positions, and then we can introduce the Schrödinger equation. So we say that the evolution is governed by unitary dynamics. So their coefficients will be controlled by the dynamics of the system. But the interesting point here is that a superposition in one basis can be a basis for another observables. So, for example, we have position and momentum. So momentum can be expressed as a linear combination of certain position bases. In our case, we have continuous Hilbert space, so it will be continuous. But yeah, so if we put coefficients in certain way, that depends on P, and X.
There is I missing.
Yeah. Yeah, we noticed. Thank you, sir.
Usłyszał i poprawił.
So this superposition principle is really.
To jest taka rzecz oczywista, nie mówiąc, że stały planka.
Okay, please continue.
Yeah. So this principle is usually demonstrated in interference phenomena, such as interference, and it is closely related to the complementarity principle, which in many of the authors have studied separately, but it is nothing but the first principle of quantum mechanics. So once we have made our mathematical structure, we have established our mathematical structures, these phenomena are implicitly embedded in that structure. So
the last one is
last
one is not true. You can have invariance of the sound waves, mechanical waves. You mean the
it's large objects in a quantum way. In a quantum way.
when you said
Yeah. Thank you.
So it's timing waves interfere.
Yeah. So we don't consider them quantum phenomena. Those are
But large objects. So if you imagine oceanic wave, which is hundreds of kilometers,
that's true.
Yes.
Yeah.
Hundreds of kilometers.
They also interfere.
So by the way, what is the largest object which was in the quantum superposition?
Very good question.
I know.
It was like 25,000.
25,000 atomic units. It was it insulin?
Protein. Yeah. Some protein molecule.
And they
You don't want another Kobe from the quantum now.
Quantum.
But they have done it. They've done it with some protein. So it's all.
25,000.
Yeah.
were thinking actually what was complementary. I didn't get why superposition principle is rooted in complementarity.
No, complementarity principle is
It's the other way around.
rooted in the superposition principle. So our in a theory we establish our postulates in a minimalistic way, and I suppose the postulates are more fundamental than these principles, and complementarity can be derived from the state description. So whenever we
You're right.
yeah. So whenever we have a state, just like the previous one, if we have just avoid the missing I. So we have P. P is the eigenstate of momentum operator, but it is in superposition of other observable eigenstates of other observable, and that's where this complementarity comes from. So one observable can be one eigenstate can be expressed in superposition of other observables eigenbases. Then the third one, then the second interesting feature comes from the composite state formula. So when we have, let's say, instead of one card, we have two cards, and the physical possibilities which can be distinguished from each other forms the space, and there will be 16 types of possibilities, 16 different possibilities. So it can form a basis for a Hilbert space, and we can write a state which is superposition of any of these states, and we see that. Okay, so we see that this state is.
There's a stick behind it, but stick behind physical object.
Okay. Yeah. So this state is it's usually known as an entangled state in quantum mechanics. So this is nothing but a consequence of composite state formalism, where we have just, so this is a superposition of two composite distinguishable states, and the system to a larger system, we get these states, and they are common. So this resulted in a well-known EPR paradox. Sorry, I didn't mention it, but this EPR paradox is what was formulated to counter certain features of quantum mechanics, such as if Einstein Podolsky and Rosen formulated that when there are two such two particles in an entangled state, one can see that the element of reality, which is let's say particles state, is in one of the eigenstate of its local observable, then these element of realities can be steered by a distant event, which can be space like separated. So that suggested that maybe quantum mechanics is not complete, and this should be supplemented with certain hidden variable theories. Then we get third, which is very peculiar feature of the quantum systems, is quantum theory, is that it predicts macroscopic superposition. Yeah, so technically have been well realized in laboratories, and it's well established. But the third one, macroscopic superposition, is still absent, and it comes from the composite state postulate and the unity dynamics of the system. So system is governed by a closed system is governed by its Hamiltonian, and when we have a composite system, we can write an interaction Hamiltonian such that the system evolves into a macroscopic superposition. For example, we have a unity interaction of this form where two spins are interacting with jet coupling, and then it just gives it, if system one is in 0 and second is in plus, it leads to 0, 0. And if it is 1 and plus, and it goes to 1, 1. So it's kind of a control unity. So if we have a multiple qubits in prepared in plus state, sorry.
Excuse me, you have 0 plus.
Mhm.
The sigma z basis would be, so what is the basis for sigma z? 0, 1?
0, 1 is standard computational basis for signal.
0 plus in the sigma z basis would be a superposition of 0,
Superposition
0 and 0, 1.
of 0 and 1.
Shouldn't it then go to superposition?
So yeah, thank you. So it's just a 0 and 0 plus for this pi by 4, it's the 0. So it will be
The sigma z is not flipping the speed.
sigma
Just giving,
sigma z flips the sigma x basis. So sigma z applying on plus will give you minus.
yes, I agree.
Yeah.
So then I have superposition, no?
Yeah. So if it acts on 0 and plus, it gives us 0 and cancel plus minus.
Okay.
That gives us 0.
Sorry.
And similarly, when it is plus and plus, so it will be plus minus minus. So that gives us 1 and 1. So now consider n such states, and we see that 0 cancel this large number of spins prepared in plus, gives us 0, cancel 0 prepared, and similarly this. So when we apply to a superposition state, which is the system is prepared in 0 and 1, 0 plus 1, it gives us a state where n spins are either 0 or 1. This is a simple amplification process. So and we can consider this as an measurement. So if it is a 0, it's a 0 and a macroscopic. N spins oriented in z plus direction can produce magnetic momentum, which is macroscopic. So it's a bulk magnetization, if you think. And this is a bulk magnetization in opposite. So it's a very simple, oversimplified thought experiment. So it's a superposition of macroscopic fields, and we can expand this to like triggering a magnet or manipulating the large scale superposition of two different directions.
What happens to qubit 0 plus? Because this is unit. On that's so sensible. So if you like to invert it, so 0 have to go to 0 and 0 have to go to plus. It's impossible in the unitary. So it's not unitary.
Yes, it will.
So it's unitary.
It's unitary.
So I see some discrepancy. Maybe I'm wrong.
Yeah,
but this is more or less what Krzysiek said. Okay. So I will express it once more. So it acts equally, it was in the same way in the first space and the second space. Yes, this unitary. You see, because this is symmetric. Okay, the unitary operator, a line above. Yes, it acts in the same. No, the unitary. Oh, this one. No,
Right.
this one. The whole unitary. The whole unitary.
Yes, it acts on.
Acts in the same way in the first space and the second space because it's symmetric.
We see that it does
So
not.
0 goes to 0 and plus goes to 0.
Yes.
So if is that other way around, if you apply other way around, so 0 should go to plus.
to 0. So it's a complete orthogonal transformation. So 0 plus, and if you apply again plus will goes to 0. So it will be identical.
Maybe there is just write it on the blackboard.
Exactly, Raj, maybe you write it on the.
So you are saying that, Marek, that you apply the second time unitary or first?
So let's do it. So let's simplify it. So we have taken time the biological. So it's the identity of sigma z and sigma z. And let's apply this to this.
Raj, maybe plus and minus, maybe the plus and minus states, so that we all know
it's
what we are talking about.
0 plus 1. When we apply this, it goes to let's see sigma z x1 it is 0, so we call it minus. So let's define it. So what we get infinity when it x1 0 plus, we get this state, and you can take it out 0, so it's a plus and minus. So you see, plus and minus gives us just root 2 0, and you will see it's something but.
You forgot root 2, but anyway,
So
let's forget normalization.
Normalization is not so important.
Yeah, so it gives us 0 and 0.
Okay.
This is you can write it.
Okay.
Okay. And it will be over there also. If we write okay. So, thank you.
Fine, thank you.
Yeah, so this Schrödinger's cat paradox captures this peculiarity in a more subtle way that when we consider a situation where a cat is packed in a box and we have a nuclear particle decaying, which triggers Geiger-Müller, which is disappearing Geiger-Müller, and the detection triggers a hammer to the poison bottle, and if it's decayed, it will break the bottle, and if it's not, the bottle will be intact. So similar to this situation,
Actually, here, usually I is missing. Usually. There will be I.
I is.
I is missing.
Always, yes.
Okay, so so we see that it's a scenario where one can predict that the cat can be alive or dead at the same time, and
Assuming that you can distinguish between these two states.
right.
Right?
This
Sorry, that's also a point. Assuming that you can distinguish between two states like that, alive.
alive and dead, yes. So it's depending on the hypothetical chain reaction that poison will lead to dead and it's not absence will lead to alive. So assuming that without poison the cat will not be dead. So that
What is the difference with roulette? You know, those roulette Russian roulette. You're bullet or not bullet, so you don't know, you're clicking on somebody's head.
Yeah.
And then after many clickings, this
That-
head
that's-
is a preposition of.
No, I think that's more classical.
Deterministic.
That's more
bullet is
that's
always
classical.
somewhere.
probably.
You don't know, but it's always somewhere.
Yes.
Mixture, not.
And
Yeah.
here you don't know.
The hammer.
So here we don't know. So, so then it opens a lot of questions that, since all objects are made of microscopic entities, which follows quantum features such as superposition, complementarity, entanglement, and are absent at microscopic levels. So the first the thing it comes from is the universality of quantum mechanics. This dictates that the microscopic superpositions are possible, and the interaction leads to a situation where at microscope operators and observers can be modeled with quantum mechanics, and it predicts that there should not be a collapse. And then so something is is it true, is it possible that something is really missing from our standard formalism, and we should supplement our mechanics, or it's just stuck with the complexity to explain the quantum to classical transition. So then it opens the question that can we explain this classical to quantum transition without reinterpreting quantum theory or modifying. So there are many efforts have been put to solve these questions, solve this problem. So first measure came from Bohm in 1982, where he supplemented quantum mechanics with hidden variables. Hidden variables are quotients and momentum particles. So particle is classically behaving, but it's governed by the dynamics of Schrödinger equation. It does remove the non-unity collapse, which is peculiar in standard quantum mechanics. But the cost is the local variables are non-local. Sorry, the hidden variables are non-local. Then Everett introduced a relative state formalism, which was later known as a manual interpretation, where everything is evolving unitarily and everything can be explained with that, just by interpreting that it's a branching of the universe. In 1780s, a very interesting approach was taken, which is considering the role of environment in explaining the quantum to classical transition. Majorly by Zay, it was pioneered, and then it was largely developed by Zurich in 80s and 90s. And one of the other approach was collapse models, where they have modified quantum mechanics in order to make it compatible with collapse as well as the microscopic superpositions. There are other candidates, but I think they are not relevant here. So now we will focus on quantum decoherence paradigm. So openness of quantum system is somehow linked to quantum to classical transition, and continuous interactions with large environment decode quantum systems, and which can be interpreted or seen as emergence of classicality. So consider a toy model where interaction is such that system's Z spin is interacting with other spins, the model we considered previously. And of course, I is missing here. So consider that in a very weak coupling scenario, the zero now leads to zero and some state which is cos theta plus sine theta 1, and 1 leads to this state. So there can be these state can be non-orthogonal, and it can have a small overlap. Now, sorry, major overlap. So it's weakly correlated. So the state now 0 plus will lead to this, and 1 plus will go to this state. But when n grows, we see that these states become orthogonal approximately. So when we discard environment, we see that this the state is written in this form, and this decoherence factor dies when we have large n. So the reduced state is now a classical mixture where this is the state corresponding to whether there is bullet or no bullet. So it's a classical mixture where particle is with some probability in 0 and some probability in 1. So now let's say so after this there was a major development. So let's see what's the shortcoming of this is that we do not yet understand how multiple observers observe the same reality about the system. So this is decoherence. We know that system decohers when we apply such interaction Hamiltonian. So in 2004, 3, 4, and 5, Zurich and his collaborator proposed a approach where we can study objectivity in a more complete way. So objective property is defined in such a way that a property of a physical system is objective when it is simultaneously accessible to multiple observers who are able to find out what it is about prior about the system of interest, and who can arrive about it without prior agreement. So center, and there are multiple observers who are trying to access the trying to gain some information about the system. So the objective property is saying that the observers, so all observers agree on the observation. And it was shown that the pointer states are the most stable states against decoherence. So if we find a system, a state which does not change with decoherence, then we say that the state which so they diagonalize in the basis of pointer states. And another requirement for objectivity is that there should be redundancy of the information stored in the environment. So
Excuse me, what do you exactly mean by many observers? All observers or more than one observer?
it's more than two.
More than two.
So Zurich defined it more than two, but it's a common sense that we should
So
expect.
already okay.
Yeah,
Two arbitrary observers.
yeah.
Well, I'm coming up because, of course, in special relativity, it's never fulfilled, but that's it. Relativity and quantum mechanics.
Yeah.
I know it's a separate issue.
Yeah, it's a peculiar word. Yeah. There also we can then the major thanks to Yara, they propose that but the state of but as this that a state of the system exists objectively if many observers can find out the state independently and without perturbing it. So there are two components. So it's the state is known to multiple observers independently. They do not need to communicate each other. And without perturbing it. So it asserts more at the fundamental. It relates this thing to the Einstein's notion of element of reality, that we know state a prior without disturbing it. So it is more closer to Einstein's notion of objectivity or reality. So then the second element is the spectrum broadcast structure, that if such state is found where this S represents the system, and E1, E2, E3, En are fragments of an environment, let's say fractions which has no overlap, then one can join these different fragments and call it a environment. Yeah. The states of these fragments are orthogonal when I is not equals to J. So when a system is in I, then all environment fragments will know that it's in I, and it's in J, then it will objectively know that it's in J. So objectivity and spectral broadcast structure. Spectral broadcast structure is sufficient to show that objectivity exists, and then it converts it also to a source, the sufficient and necessary condition for describing the objectivity. Yeah. So and SBS form Theor decoherence models such as spin quantum Brownian motion and dielectric limited spheres, where it has been shown that quantum objectivity emerges from the quantum world. And more realistic states have been studies where the assumptions on the initial states of environment have been relaxed. However, all the models a preferred system observable during the intersystem. So it somehow generates or it's a it is a requirement for the emergence of objective quantum states commute with these states. We say that it's objective. So assume a scenario where there is more general interaction scenario where every spin, let's say every sub of the environment is interacting. It's very, but the coupling observable is also varying. But it can be argued that these interactions will never lead to a counter state. because the pointer state, we need pointer state to this interaction Hamiltonian. And this scenario we may never pointer state. So it's a flow like state maybe to mix it. Another point we must discuss the spin boson interaction models shown to emerging position basis. While in classical world, we always see that objectivity is surprisingly always position basis. So let's consider thought experiment where we show that somehow this question, these two questions can be answered. So let's consider a single spin half particle which is shared with two laboratories, and it's note that it's not two particles; it's a single particle in superposition of two positions, and it has some internal degree of freedom. We call it spin right now. And Alice now wants to say, so this composite state of these S, I, and A is written, can be written as this. Then Alice performs a unity where there is a identity on the spatial wave function and identity on spin if C wants to send 0, and if C wants to send 1, C applies a bit flip on spin part and does not disturb the spatial wave function. These kind of operations are mathematically feasible, and they are often used in operational quantum mechanics. Then Bob made the Z component of the spin of her part, of his part, and it can be said when it is A0, and state the Bob will immediately know it's one. So now the state correlated because of certain unities. Similarly, they can just use a measurement setting where Alice performs nothing if he wants to send a 0 and performs a measurement in plus decimal x basis on a spin. Not the function. It immediately leads to a correlated state and 0. So it somehow violates the no faster than speed of light communication principle. So where are we wrong? What are we doing? So simple solution is maybe we should not the solution is that we consider unities whenever there is a manipulation on internal degree of freedom. We consider the information of the location of the laboratory. So we have to always consider a project kind of scenario on the position basis. So now this unitary and this measurement setting is valid and compatible with the light communication. So even though Alice was trying to manipulate spin degree of freedom, but she is bound to disturb the wave function of the particle. And this hints us to drift or other scenario. So another, it is very simple, but it has a very profound implications that all the interactions should
previous measurement next.
it's a somehow restriction on our hands. We are not allowed to use unattended. Yeah. Now consider environmental is superposition of d different locations. And the wave function can be written in the coherent superposition. The direction we have in this form possible scenario. So this is the interaction unity on the spin. So this is the particle, and let's consider that there are certain spin particles located near this location. So they will always interact with this part of the wave function, and similar in all other cases. So we index these environmental. So these are all spins. So we index it as 1, 1, 1, 2, and so on. So this unitary is interaction between spin of system and spin of K spin environmental subsystem. And then since we cannot leave a function unattended, so there should be some between the spatial wave functions of particle. This is the simplest Toy model we have of this form. And here we can relax this assumption that spin can be arbitrary. Spins can arbitrarily interact with each other. We do not need a preferred spin for the interaction of the system. And we see that
Strictly or independent degree of like spin and the wave, like spatial wave function, you cannot just describe the particle with tensor product with different independent degree of freedom. That's why you have to disturb the spatial wave function even if you measure the only spin projection of it.
It's just coming from that the interaction should have some information, leave some imprint about the location of the interaction, where it's happening. Just yeah, so we consider system and environment interaction. And we see that when we constitute microscopic party, so we write that the interaction can be considered without loss of generality, that each spin but the spin is 0, particle is collapsing in A, spin is 1. or it's collapsed in B. So there are three outcomes. And when it's collapsed in B, its spin will be unchanged. So it will be initial spin, and Bob will get no information.
Okay, second question. Because your result shows that any wave function needs to be considered with the spatial wave function.
No, so like it should be considered when we consider interactions with internal degree of freedom, spins or energy levels, anything.
Yeah, anything. It means that the spatial wave function is very special.
Yes.
How do you use your result to reinterpret the EPI experiments? Because in that case, we don't consider the spatial wave function. But here you say that all wave function needs to be to include the spatial wave function.
Right. So the EPR scenario is a bit different because there are two particles located in two different laboratories. However, my argument will be applicable to that. If we carefully model EPR, it will be valid. But EPR is not a paradox which concerns this kind of situation. It's more fundamental to element of reality.
Okay, I think our time is up. So if there are more questions, we invite everyone, of course, to the coffee roasters. So let's thank Rajendra again.